Okay, thank you for the invitation. This is a great meeting and a great opportunity. I shall speak first. I'm Jean-Claude Risset, and then Richard will continue, because my presentation will be sort of a reminder, excuse me, of early sonic representations, and then the encounter with wavelets in Marseille in the 1980s. So, first, a little about the physics of sound. Now, sounds can be recorded now, and they have first been recorded in the 50s, 60s, and they can be reproduced in the absence of their acoustical cause, which is a vibrating system. And so they can be reproduced. Usually people think of Mary had a little lamb by Edison as 1877, but actually I will play something that was recorded in 1860 on a paper with carbon, and it has been only recently turned into a readable groove that was then converted to electricity. And so this is Scott de Martinville, Au clair de la lune. So that's 1860, but it was not reproduced immediately. It took more than a century. So verba volant and scripta manent is no longer a true statement. Sounds can be converted into electric signals, so they can be dealt with electrical technology, in addition to being capable of being reproduced, studied, played in reverse, etc. So that was relevant to music. Olivier Messens said, or wrote even, that the advent of electricity in music is the most important event in the 20th century. Hugues Dufour speaks about the electrical revolution. Now, the electric revolution has several ages. The electrotechnical age with transformers. This is a patent of 1997 of Cahill, a sound dynamo, dynamophone, or telharmonium, because it can also be heard at distances over the telephone. And it weighted 300 tons, and it developed very well, except at some point went broke because the telephone system refused the access because there were leaks, and supposedly some ladies said that their boss was saying he was at the office, but they heard music, so he was in bad places. Now, Lee de Forest inaugurated the electronic age, and it's not well known that his first patent for the triode was called the Odeon, and he wanted to do electronic instrument, which he did finally in 1915. This was improved by Theremin and Martineau later on, and this was used with electricity serving as instruments, and then radio studios were diverted from their primary use to do experimental music, musique concrète in Paris, electronic music in Cologne and Munich, and also in both of them in New York, Columbia, Princeton. And then the next step was a digital age, and computer synthesis was inaugurated by Max Mathews in 1957, first computer synthesis and first digital sound recording, before the invention of the laser. This is Max Mathews, John Miller in the stack of cards that was a program to synthesize music, a modular program. What you see below is not a computer, it's just the digital to analog converter. The computer, an IBM 1790, was much larger than this amphitheater. So this is a representation of sound waves, and these waves represent these sounds. So these sounds have the same amplitude Fourier spectrum and different phases, And as Stéphane Mala indicated before, but in the other way, a slight deformation of this wave induces a fantastic change in the frequency width, for example. If you have a wiggle, then you have a very wide spectrum, and the ear hears this very strongly. So time domain representation are not very intuitive because they are far away from the way the ear sorts and differentiates sound. All these waves sound exactly the same, so I won't play them. Now, Fourier series was very useful, and of course harmonics were considered, you know, part for periodic sounds. For non-periodic sounds, of course, it didn't work quite well, and Helmholtz didn't really know that because he had these graphs of waves, and so in this space you had maybe hundredths of a second, so there was not much change in the wave, and he assumed that the wave was typical of the timbre, of the identity of the sound. But clearly, Fourier transform conveys even the information even for variable sound, but it doesn't show. It's convenient to describe the effect of linear invariant filters. And, but clearly, one needs running analysis similar to what the ear does. And the sound spectrograph was developed during the war quite secretly because it was meant to try to analyze voices and etc. And so the article was published in 1946, but it existed long before. And that's very close to Gabor representation in terms of finite, compact, basic molecules, I mean grains. And Gabor remarked that it's a little ridiculous to want to represent a time-limited function in terms of infinite length sine waves, so they have to interfere out of the domain of existence of the sound, so it's very complicated. Now, the granular idea of Gabor was remarked by Xenakis and put to action by Curtis Rhodes in 1978, but he didn't do any real reconstruction. These are, by the way, these are sound spectrograms, which are in effect short-term Fourier analysis, running analysis. Well, let me see, for example, this one. You will see after a little chord, you will see the harmonics going up like so. Let's see, I think. Now this one is another type of sound. Now it goes on, and it can go, it already gone back to its starting point, so it's an indefinitely descending sound. And these are Fourier synthesis, but not used to reconstruct a wave, but done to grow a contour, to draw a contour, a complicated contour, thanks to the Gibbs phenomenon, which is used then for modulating the frequency of these tones, etc. So these are sonographic representation. Let me show you briefly another one, which shows the spectrum, and at the same time we'll hear the sound. That's for part of a piece of mine, and you'll see mostly the frequencies, but in fact there is information on the timbre as well. So it's time frequency, of course. So spreading frequencies and going back. Now we'll have now these are sort of putting harmonics apart. So that's an harmonic arpeggio. Now this is a sort of fractal sounds. I wouldn't speak of wavelets because not really oscillating, but etc. Well, I'll stop there. Oh, thank you. Now, this is a completely synthetic piece called Mutation that was done in '69 at Bell Laboratories. Now I'll go back to the PowerPoint if I can find it. Probably I closed it, so I'm sorry about that. Yeah, it's there. Okay, I have simply to find it. Yeah. Well, okay. Now, about processes of synthesis briefly, we'll speak mostly about signal modeling method because the physical modeling tried to model, to implement rather a physical model of vibrating system and simulate it on a computer. The signal modeling methods really calculate an approximation of the sound waves through calculation, and mainly there are three main methods: additive synthesis, adding harmonics or spectral line. For example, a bell is not harmonics but spectral lines. Formants, like in speech. Subtractive synthesis, filtering out what is not wanted, like a sculpture, remove the stone around this sculpture. And nonlinear methods, which is a way to distort so as to completely change the sound and to, for example, if you distort a sound wave, you bring harmonics into it. And so reconstruction of sound wave from analysis is very interesting because then you obtain data for synthesis. You can also produce interesting variants. For example, if you record a speech sentence, you can slow it down without or speed it up without changing the formants, and then you'll be able to still understand it. You can also denoise, reduce the information rate. Now, as I said, in the Fourier transform, the time evolution is obscure. In running analysis, this was done for quite some time, even before the digital era. For example, in Johns Hopkins, there were damp sine wave and analysis and reconstruction by Huggins or Dolansky in Harvard. Rodet later used that in Informatique, and this was called Prony methods later on. Of course, Prony never used it for sound. Linear predictive coding, which is the adaptation of the parameters of a filter. Now, the first one was additive synthesis. This is more like subtractive synthesis. This is well adapted to speech, and it can actually, it's a complete system as I understand it, but when the sound is not speech-like with a well-defined format, there is an explosion of information. The Walsh-Hadamard expansion is also computationally simple. It turns in terms of kind of square waves, but it lacks what we call graceful auditory deterioration. That is, when you do the approximation, you are far from the, if you try to approximate a sine wave, then you have all these angles, which of course introduce lots of harmonics, so that's not a good method for sound. Now, the proof of completeness of Gabor grains was shown demonstrated by Bastian in this term of signal analysis, signal processing, and it had been already demonstrated as part of quantum mechanics by Barry, Grossmann, and Zach a few years earlier, and I think quite independently. Now, about wavelets and sounds, thanks to Daniel Kassler and Mohamed Mekboud, I had worked with computer synthesis at Bell Labs from 64 to 69 with Max Matthews, who was the founder of computer synthesis and processing. And in Lumini, I founded the Laboratoire of Informatique Musicale, working on the synthesis of musical sound and the analysis by synthesis of auditory perception. A few years later, Bernard Nérol welcomed this laboratory as part of his Laboratoire de Mécanique et d'Acoustique, LMA, and I took a leave to start synthesis at IRCAM from 75 to 79. Now, in the 80s, Jean Morlet proposed the use of the Morlet wavelet for analyzing geophysical signals. Alex Grossmann realized that the Morlet analysis was inversible, and in fact that it worked with a lot of possible oscillatory functions that were limited in, well located. And so that was the generalization of the analysis synthesis of terms of wavelets of constant arbitrary shape with mean value 0. I think their first publication was 84 and 85. Now, my own role was simply to be the interface between Alex and our lab in LMA, which was also in Marseille. Alex was then at the Centre de Physique Théorique, which is there, I think, yeah. So I met Alex and mostly, of course, Richard. We will present the early realizations. So I discussed with Alex Grossmann, Jean Morlet, and Thierry Paul in 84. In April 1985, I wrote a project so that the LMA would participate to a RCP, Recherche Coopérative sur Programme, describing the interest for sound research and the equipment available at LMA, and proposing that Richard would work with Alex Grossmann to perform wavelet analysis and synthesis of sound as part of his thesis. Daniel Arfib had the CNRS position, and Richard was then financed by Anvar, LP Innovation. Shortly after, there was a substantial grant from the Navy, DGA, Direction de l'Armement, contracted with LMA to implement a real-time sound synthesis system on the audio processor CITER, which was then at that time extremely expensive. CITER was designed by Jean-François Louis of IRCAM, and it would speed up the computations considerably. So Richard Kronland exploratory research with Alex Grossmann was important, and I will let him sum it up, but I would first like to present 3 examples related to wavelet research. Alex Grossmann recorded a sentence oh, excuse me. I'll start again. Now, from Alex's recording of Gira, Frédéric Boyer performed a reconstitution. He used 12 wavelets per octave, and he performed a defective synthesis so as to harmonize the Gira as a major chord, minor chord, dominant sevenths, or minor sevenths, diminished seven. I'm sorry, that's a mistake. Major, minor now. Dominant sevenths and minor sevenths. And Daniel Arfib used Gabor grains to stretch Alex's recording, keeping the speech intelligible by stretching only the vowels. I forgot to say that the reconstruction of Alex through wavelet or Gabor was identical. The waves really coincided, so it's impossible to distinguish them. Now, there were other applications. In particular, Philippe Guillemin developed, from using the wavelet, a way to extract spectral lines for additive synthesis, pseudo-periodic or even bell-like sounds. Specific applications, of course, required specific users of the wavelet transform. It's not just a magic thing that will do everything. It's a representation, but there has been a lot of work since. For example, to reduce information for quasi-periodic, Wickheiser and Grossmann had to use wavelet packets. So I shall end now with a 3-minute excerpt from a piece Invisible, which allies acoustic sounds and digitally processed sound, taking advantage of early wavelet research. It's called Invisible. The soprano that we will hear is Irene Jarski. So first we hear encounters between the voice of the soprano, more and more stretched in time, and synthetic voice-like tones. Then there is a little passage where you hear minor bell tones and artificial major bells. Then to conclude, the hybridation of the spoken voice and the noise of the wind.
Il y avait une différence. Une sensation de vide. Respire, cela s'appelle le vent. Le zéphyr produit une harmonie mineure. La bourrasque, une harmonie majeure. N'écoute pas par tes oreilles. Mais par ton esprit. N'écoute pas par ton esprit, mais par ton souffle. Le souffle.
Voilà, je vais passer la parole à Richard. Merci.